Now I'd like to introduce our final speaker, Abby McConnell, University of Leeds.
Thank you. Hello, I'm Abby. I'll be talking about some work I've done recently looking at the HO2 uptake on secondary organic aerosols. And I work in the chemistry department at the University of Leeds. So why do we care about HO2? So this here is the tropospheric hot cycle. It's very important in atmospheric chemistry, and it kind of shows some of the reactions which are important in our atmosphere. OH and HO2 are kind of closely linked in this cycle by the conversion of CO and NO, and they are collectively called HOX. We're quite interested in OH as it's the main kind of daytime oxidant in our atmosphere, and it determines the lifetime of many gas-based species, including kind of greenhouse gases like methane and VOCs. We also need to kind of understand its production and destruction of both HO2 and OH, so we can predict the concentration of other kind of secondary pollutants, such as kind of SOA and ozone. Another important reason why we care about HO2 is because there's sometimes a discrepancy between our HO2 measured and our HO2 modeled. So this is kind of an example here of campaigns worldwide where our model concentrations of HO2 are actually higher than our measured. So this means that we have a missing link in our models where the HO2 is being destroyed, but we're not quite sure where. Research has kind of shown this is due to heterogeneous uptake onto aerosols, and current research is kind of focusing on that and quantify this so that we can include it into atmospheric models. So what happens when we get heterogeneous uptake onto aerosols? So a lot of processes have to occur for us to kind of get uptake. So first of all, we can kind of get gas-phase diffusion to the surface of the aerosol. And then what happens depends on kind of the phase of your aerosol and what type of aerosol you have. So for example, if you have a liquid aerosol, you will get solvation, diffusion into the bulk, maybe reaction in the bulk. But if you have like a solid aerosol, you'll probably only get reaction at the interface, or you can just get absorption and desorption where you don't kind of form any products. We define the uptake by this kind of uptake coefficient here, so gamma, and that can be described to describe the rate of loss of HO2 onto the aerosol, and that kind of is in the range 0 to 1. So that's kind of what we do, including models. If you kind of look at the current literature from all laboratory field and modeling studies, it can span several orders of magnitude, so between 0 and 1. So I'll just give you a few examples. So this is a kind of campaign that happened in China where they took those samples from 2 different mountain sites, and then they took those and kind of did offline measurements of HO2 of those filter samples. And as you can see, the uptake there varies drastically depending on the 2 mountain sites. They were actually measured in the same kind of physical conditions, so it was thought that this difference was due to kind of different constituents within the aerosols. And then there was another one with a campaign in Yokohama, Japan, where they kind of measured HO2 online this time for like the whole series of the campaign, and it varied from 0 to 0.4. So it kind of shows that physical conditions were kind of changing, so the relative humidity would be different day to day, but they also thought there could be metal ions present, which can increase your uptake as they kind of work to catalyze your HO2 uptake. So currently in models, the go-to HO2 uptake to use is 0.1. However, we do kind of need more systematic measurements, so more kind of lab-based studies to kind of say, actually, you've got this type of aerosol in your kind of campaign. That means you need to be using this, and we should not really be using a base of 0.1. It depends on what kind of constituents you have in the aerosols. So why did I choose secondary organic aerosols? There's actually limited measurements on the uptake of HO2 on secondary organic aerosols, which I think I might know why now, but models indicate that the main fraction of organic aerosols is secondary in nature. So a little reminder of how SOAs are formed. So you kind of get the release of volatile organic compounds from both biogenic and anthropogenic sources. These are then oxygenated to lower vapor pressure products. They can condense on primitive system particles or grow through nucleation and growth. And then grow by condensation growth. So how do we make them in the lab? So we use a potential aerosol mass chamber, which is also sometimes called an oxidative flow reactor. So it's quite small, it's only 16 liters in capacity, and it kind of has these characteristic kind of 254 nanometer labs in it. But what it does is it uses an excess of oxidants, so you make the maximum amount of aerosols from your precursor VOCs, which is kind of entered for a bubbler here. You can do ozone oxidation by using that kind of mercury lamp there, or you can kind of turn these lamps on inside the chamber, and then you get OH oxidation. This is also really good because it makes aerosols in, a matter of minutes instead of days, kind of what you'd have in atmospheric conditions. You have to do several steps to kind of get your aerosols ready for them to enter the flow tube. You have to remove any kind of gas-based species because they can cause an interference in your laser-induced fluorescence cell later on. You kind of have a water bath and conditioning tube, so we can change the relative humidity inside the PAM chamber. So it just allows our kind of aerosols to condition to that relative humidity. We then have an aerosol impactor, so it removes any aerosols above the size that we can measure on the SOPS. Then we have the filters that allows us to change the concentration of aerosols, which go inside the flow tube. This is just kind of the example of a different size distribution using two different precursor VOCs. So the blue one is alpha-pinene, and the orange one is trimethylbenzene with the same amount of oxidant present ozone. So you can see you just get slightly different aerosol size distribution depending on which precursor VOC you use. So this is the flow tube it needs. So it's just this long glass tube, and you can kind of see that at the end there we've got a laser-induced fluorescence cell. One way again. So this is kind of a diagram of how it works. So we kind of got our aerosol generation, which is our PAM chamber. We then get our SOA and it flows through the chamber. And then we have this moving HO2 injector. So HO2 is made kind of at the end of the injector, where the photolysis is water. And then the HO2 injector can move backwards and forward, which allows us to change our residence time of HO2 and how long it has to react with those secondary organic aerosols. We then can measure our HO2 in a phage cell, so that's fluorescence assay by gas expansion. So first we convert it to OH by NO, and then we kind of probe it with a 308 nanometer laser and measure the fluorescence at the same wavelength. Our SMPS can be used to measure the kind of aerosol size distribution at the start and the end of the flow tube, so we can see if there's any differences in the aerosols. And we can also measure the RH and the temperature within inside the flow tube. So first of all, what we need to do to kind of do an uptake experiment is we need to work out how much H2 is lost by the wall and in the gas phase. So you do kind of this like decay with injector distance with only H2 present. You then add your aerosols and you do it again. You then do it at various different aerosol surface areas. So as you can see here on this blue line, you've got a slightly bigger aerosol surface area. So you actually get a bigger decay in your H2 and there's more surface area for your H2 to be lost. You then do some kind of first order kinetics, so you've got the LM of HO2 signal against your exposure time, and you do this at lots of different aerosol concentrations to kind of get a graph a bit like this. And then from that, you can get your Y-off, so your observed uptake coefficient, which is what we're trying to get out of this to include these models. So first of all, we wanted to do the HO2 uptake onto trimethylbenzene. We kind of picked this because it's an SOA that is the HO2 uptake has previously been measured on. And we wanted to focus on trying to see if there's a humidity dependence with HO2 uptake on trimethylbenzene. It's been shown here, so this was for copper doped sucrose aerosols. So as the relative humidity increased, you got quite an increase in your HO2 uptake as the aerosols kind of took on more water and became less viscous, your HO2 uptake more readily. So we wanted to try this at various different relative humidities. So first we started off at relatively low humidity, so that was 36%. As you can see, we've got quite a low uptake coefficient. This curve is quite very scattered because we're kind of close to the detection limit of our equipment here, but we've kind of got a low uptake coefficient. So we wanted to then try and increase the relative humidity. Again. That's what we did. And with this one kind of graph plot also includes the one I said previously that was taken on TMBS where at 50%. As you can see, at the range of relative humidities we tried, there didn't seem to be any difference in the uptake. They're all fairly low, kind of close to our detection limit. It wouldn't really make too much of a difference if it was included in the models. If we kind of focus on the kind of aerosol size distribution at these different relative humidities, you can kind of see that it doesn't change much. You don't seem to get a massive shift of the aerosol taking on more water. So this might be trimethylbenzene might not kind of be taking on much water, so it's not having a lower viscosity and a higher uptake coefficient. We then tried limonene SOA, so we kind of did that with ozonolysis, and we tried again a range of relative humidities. This you can see even more, there's just scatter, there's no kind of increased uptake there as you kind of have increased aerosol surface area, and it was all below the detection limit. So this is kind of similar to previous work, which is showing that there's an undetectable uptake observed for accompanying SOA from both OH and ozone oxidation. So not too surprising. So kind of in summary, I measured relatively low and sometimes undetectable uptake onto single component SOAs, so in this experiment, trimene, benzene, and limonene, and there was no observable relationship with relative humidity. This at first might seem quite disappointing, because it means that this is not the reason why we kind of have this missing syncopation too, but future work will kind of look at more atmospherically relevant SOAs. So these are only single component. In the atmosphere, you're unlikely to get single component SOAs. You're more likely to have C particle to which the SOA kind of condenses on. So we know that there's some C particles, such as ammonium sulfate, that already have a high uptake coefficient. Now we know that SOA has a low uptake coefficient. What would happen if our organic coating in that SOA grew around that ammonium sulfate? Would it have a higher uptake coefficient, or would this kind of organic coating kind of block any kind of HM2 uptake? So that's kind of what the work will focus on next. And thank you for listening. I'll be looking to the group leads, some funding, and any questions.
And any questions?
Hiya. I just want to say congratulations on some really fantastic work there. I know the uptake coefficients are low, but that's a really interesting and important step forward for our understanding of
Thank
the
you.
Thank you so much. In the early days of this type of study, Cooper and Abad showed that the reaction was bimolecular in HO2, so it's a kind of self-reaction
Yeah.
in aerosol. Did you perform any concentration dependent studies to sort of investigate whether there's a
We did kind of look at some decondensation, but we did do some concentration studies, but we were actually finding that kind of the more HO2 that we added, we were just getting a dominant loss in the gas phase. And we did do some modelling studies to kind of look at that, but at this point it was because we had such a low uptake, you couldn't kind of increase your HO2 too much, because then that loss was just dominating. We weren't seeing any uptake. But yeah, no, that's an interesting point. Thank you.
Any other questions? May I ask, how did you calculate the one-offs?
So you kind of do, so you kind of look, so you know kind of what kind of, I guess I do have it on the slide, but I don't know if it'll take too long to do that. So you're kind of doing this, but without your aerosols present. So you get your wall loss here, and then you just do the same thing. You just plug your ln of HO2 against your reaction time, and then you can work out your wall loss, which also combines your HO2 gas phase loss as well. Thank you.
Okay, well, thanks again, Abby.
Thank you.
Thank you to all the participants.